So let's have a quick peek into the weighted graphs programming. So here on the screen I have the undirected unweighted graph program ready on my editor that we did from the previous videos. What we want to do is we want to convert it into weighted graphs. So so add vertex is a very basic functionality and it does not differ whether it is a weighted graph or an unweighted graph. So the function remains exactly the same. However, to add the edges over here, we need to make some changes so that these edges are the edges of a weighted graph. So what do we need to do is instead of simply just appending a vertex, we need to append a dictionary which will contain a key value pair of node and vertex. So node contains the corresponding neighboring vertex to which it is connected and a key value of weight which will take the value from the argument. So I'll add an argument wt for weight and it will be the weight of the edge. So if the user says a and b are connected, two vertices, two vertex 1 and vertex 2 are connected by an edge of 20. So we need to add that information while we are creating the edge. So now since this is an undirected graph, I need to do the same for the vertex 2 as well, but it should be connected to vertex 1. So node that is connected to is vertex 1 and the weight remains the same. So the remove functionality, the remove edge and the remove vertex are not actually used often in the graph data structure. So we can actually just skip that part. However, if we were to do it, we would have to do, the complexity would have been increased because we would have to iterate over the list and check if the dictionary has a node value of the corresponding vertex, and if it does has, then we would have performed the remove operation and it would have costed more than it is currently now. But uh, I think it's a better idea to remove both the functions altogether because in the graph data structure and especially from the point of view of interview preparation and the question solving, we barely ever use the remove functionalities. So yes, let's remove them both altogether. So let's actually take a moment to test this out. So I'll create an object G of the graph, and what I will do is I will add vertex to it. So the vertex I want to add is, let's say, A. So I'm going to add another vertex now because uh, at least two vertex to test it out, I guess. So B, I'll name it. And now I want to add the edge between the two vertices. So what I will do is I will use the add edge functionality. I'll I'll insert the that I want edge between A and B, and the weight that I'm looking for is, let's say, 20. So this will add an edge between A and B of weight 20 units. So now let's make use of the adjacency list. So what I will do is I'll make a call to adjacency list and I'll specify that I'm referring to the node vertex A, and I can't do anything here. So I need to like do an iteration in this list. So first of all, it should be g dot adjacency list because g is our object. So for I in g dot adjacency list of vertex A, so v is a better choice instead of I because v stands for vertex, so it makes more sense. So let's print the information that we are obtaining. So I'm going to print the node and the neighboring node, right? The node to which we can connect. So I'll pass a string. So the neighbor node and followed by the neighbor node. So to obtain that, we need to do v and pass the key as the node, and the other information that I want to print is the weight, right? So I'll print the string weight and the following weight. So v followed by the key value that is weight. And now I'll run the program. So yeah, we have the output as node neighbor node as B and weight as 20. So for A, the only neighbors, we iterated the entire list, but for A, the only neighbor that A is connected to is B, and the weight, corresponding weight is 20, and that got printed on the screen. So that is how the weighted graph works, and the self-adjacency list makes sense while interpreting the